Hello and welcome back to Introductory Electromancy. Today we will be talking about the relay. If I were doing these in the order that they were developed, I would have covered relays before transistors. But I'm doing them in whatever order I feel like. So, what is a relay? It is a type of electrically controlled switch. Now, I'm going to start by demonstrating an electromagnet, which you, dear viewer, can make at home using copper wire and something ferromagnetic. In my case, this very sad-looking nail. It's important to note that this is enameled copper wire, and that if you try and use bare copper wire, the coils will short out and you won't get the effect that you want. But to make an electromagnet, you just need a ferromagnetic core to concentrate the magnetic field and a bunch of turns of wire that is insulated around the core. This is something that I should have done in my description of the inductor, but I did not. So, have an electromagnet. If you are doing this at home, you might not have a lab power supply. You could use a D battery or something similar. So, I have placed the second nail close to the first one. I have a power supply. And now, if I apply power to my wonderful contraption here, it should turn into a magnet when power is applied. So, you can see now it is an object with a magnetic field, and if I disconnect power, it stops being a magnet. If you want to reverse which pole of the induced magnet is the N or the S pole, you would simply switch the polarity. Now, this is interesting enough, but what practical use does it have? After all, why are we doing anything if it does not have a practical application? Well, this itself can be used in places like scrap yards, where you need to be able to pick up some sort of magnetic object, scrap steel, for example. And then release it by disconnecting power to the magnet. But another application of this is to use the resulting magnetic field to pull a switch contact. So you can use a current through the loop of wire to force a switch to close, which lets you use a smaller current through this loop of wire to control a larger current through the switch contacts. And that is the principle of the relay. Now, I have a few relays to show you, dear viewer. This one is from Radio Shack, which is no longer in business, but because I was born in the last millennium, the one with Marco Polo and Genghis Khan, I had the opportunity to purchase parts from Radio Shack before they cease to exist. This one came like this. It was in a scrapyard, and someone attempting to remove it had already torn off the casing, which is convenient because it lets you see the inner workings. So this is a 12-volt relay, automotive. I believe it came out of a Subaru. I do not remember the model. But in this beautiful cutaway view, you can see the coil with windings and the contact here, which can be pulled up by an applied current through this coil. So this relay has two contacts. You can see on the bottom is the normally closed contact, abbreviated NC, and at the top, normally open contact, abbreviated NO. And when you apply a current to this coil, it pulls the moving contact in the middle up, which opens the connection to the bottom contact and closes the connection to the top. So this is a 12-volt relay. My power supply is set to provide 12 volts. Let's see if I can record this well enough. You can see when power is applied, it pulls that immovable contact up, closing it against the top. When power is removed, the spring on that contact pushes it back down to the normally closed contact. Now, you'll note, when power is applied, you hear a click. And when power is removed, you hear a click. Most electronic devices that make a click noise when they are turned on or turn themselves on do so because of an internal relay, something like this. Common examples would be an electric oven, electric heaters, air conditioners. Generally, anything that needs to control a large amount of current will use a relay. And if you hear a click when it turns on or off, what you are hearing is that internal contact moving. Now, things to know about relays. Compared to transistors, relays are slow. Because it's a physical piece of metal that has to get pulled by an electromagnet, conventional relays will only be able to switch a couple dozen times in a second. Other things to note: switch bounce. The relay, when this electromagnet is energized and it pulls that center pole up to the normally open contact to close it, it'll hit that contact and then bounce a few times. So if you have an application where you need the contact to close once and not bounce, for example, if you're counting the number of times that it switches or if the relay itself is connected to an inductive load where switch bounce would cause sparking at the contacts, the relay might not be your best choice. In the past, you could get mercury-wetted relays that had a little blob of mercury so that when the switch contacts bounced, the mercury would maintain the electrical connection. Well, they worked, but mercury is toxic. And so, dear viewer, you can no longer purchase mercury-wetted relays. At least, not that I know of. Another thing to note is that for relays, usually the common pole is labeled C, the normally closed pole is labeled NC, and the normally open contact is labeled NO. This conflicts badly with some other uses of these abbreviations. For example, in a semiconductor datasheet for a chip, in this case the ESP32, you also see the abbreviation NC, but here it means not connected. So for relays, NC means normally closed. For most chips, it means not connected. This pin is not connected to anything. Whereas here, this is the common pole, this is the normally closed contact. Now the symbol for a relay is something like this. You will see variations of it, but generally this here indicates the coil, and then you associate it with the symbol for a switch. The tab guide uses a slightly different variation. This is the coil, this is the associated switch. You will note that there is a diode listed here on this schematic. That diode is called the freewheeling diode or the flyback diode. This is because, being an electromagnet, which is an inductor, when you start running current through this coil, it produces a magnetic field, and then when you disconnect the current supply, that magnetic field collapses, inducing a spike of voltage. That spike of voltage will destroy semiconductor switches that you are using to drive the relay. So, the purpose of this diode here is so that when this is turned on, this transistor begins conducting, current begins flowing, all is well. When this transistor turns off, there is still a magnetic field here in this coil, and as that magnetic field collapses, it will want to keep current flowing. The diode allows it to keep current flowing as the magnetic field dissipates and prevents it from creating a spike of voltage which would otherwise end up across this transistor, potentially damaging or destroying it. Relays. Fun time. An electromagnet that pulls a switch. If you want to drive a relay with a semiconductor switch, make sure to use a flyback diode configured like so. Relays are slow. Relays have switch bounce. Relays make a distinctive click sound, which you may have heard while operating your own electrical appliances. That's all for now.